Chapter 6, problem number 44. A person starts from rest at the top of a large frictionless spherical surface and slides into the water below. At what angle theta does the person leave the surface? So he starts from rest. So we have the energy at A is potential. So we have mg, and then we have to figure out the height. And I suggest that we call this the zero potential energy level. Let's see what happens. So if we call this the zero potential energy level, then the original potential energy is mgr. Now over here, his energy would consist of kinetic energy, which would be 1/2 mvb squared, plus potential energy, which would be mg times this distance here. And wouldn't that distance be r times the cosine of theta? So this angle here is equal to that angle there. So r cosine theta. Okay, so first of all, we see that the mass cancels. Now, how about VB? Well, the object is in circular motion here. Since the normal force is 0, the net force is weight. And the center-directed net force would be weight x. So from Newton's second law, isn't weight times the cosine of, let's see, cosine of theta, all right? So this component here, okay, this is the hypotenuse. So if you take the cosine of theta, that's equal to weight x over weight. Yeah, so weight x is weight cosine theta is equal to the mass of the swimmer sliding down times VB squared all over R. The weight of the person is mg. Mass appears in both terms. So solving for VB squared, I get RG cosine theta, which I can substitute into this expression here. So we get RG equals 1/2 RG cosine theta plus RG cosine theta. So that is equal to 3/2 cosine theta is 1. Right, because the r's cancel, the g's cancel. So we have 1 on this side, and we have 1/2 cosine theta plus cosine theta. So that's 3/2. So cosine theta is equal to 2/3. So theta is equal to 48.2 degrees. Let's test this with a demonstration. Watch.